I would like to start with the challenges of neuromorphic AI. And so we know that neuromorphic AI has immense potential, but when it comes to deploying deep spiking neural networks on neuromorphic hardware, then the challenges start to pile up. Essentially, if we are going to use as target hardware, the neuromorphic hardware, because we know that these hardware have memory constraints and they require reduced precision during runtime. And what makes deployment possible is the use, for example, of techniques like quantization, but these techniques often overlook critical factors like the neuron firing threshold. And so one main question is, how can we reduce the memory usage for spiking neural networks while at the same time maintaining a good accuracy? And so looking back to the deep learning community, we have the luxury of using directly full precision models, but when we are working with the neuromorphic hardware, we don't have that luxury because the quantization is not like a preference, but actually a necessity. And that comes with trade-off because when you have the model and then you reduce the precision, you will often get accuracy loss. And so the main goal that we try to find in this paper is how to find the balance between the memory saving and the model accuracy. So now that we've discussed that quantization is crucial for enabling an efficient end-to-end deployment of spiking neural networks, the question is how to go about this. And for this, we have explored two quantization schemes, which are the post-training quantization or PTQ and the quantization over training or QIT. And so starting first with PTQ, as we can see that as the name suggests, the model starts first with training and then we have validation testing, and the quantization only occurs at the late stages. And this makes this method computationally efficient, but it comes with trade-offs also, because the model was actually trained in full precision and the quantization only occurs during runtime. So this itself raises the question of, can we do better than post-training quantization? And the answer is yes, with the quantization-aware training. And so for the quantization-aware training, the quantization occurs early in the training, meaning that we allow the model to adapt to low precision constraints early from the start. And one key feature of QIT is that it uses the integer 8s in the forward pass and the full precision weights in the backward pass, meaning that the activations and the weights and biases are only quantized during runtime, and the full precision is retained for updates. And this is what makes QIT computationally the computational cost very high, but at least it makes us achieve low accuracy degradation. This also raises an important question, which is, are there any other critical factors that we should account for during quantization to ensure that our models are effectively implemented on the neuromorphic hardware? And so to understand the challenges of the quantization, it is important to also understand the target hardware, which is in our case, the Spinnaker 2. So the Spinnaker 2 chip is a neuromorphic chip that has 152 processing elements that features ARM cores, DNA accelerators, etc. And these chips are then scaled up to build the SpinCloud board that has 48 Spinnaker chips. And this is ultimately scaled up to form the SpinCloud machine, that is a large-scale machine hosted at Dresden with around 5 million chips. And so looking at the unique architecture of Spinnaker 2, that means that quantization should not only account for the accuracy, meaning preserving the accuracy, but it should also account to these architectural features of Spinnaker 2 to enable a true efficient deployment. Understanding the hardware also requires understanding the software that makes the computation on Spinnaker 2 possible. And this is the software stack that runs on Spinnaker 2. And it has like the generic compute software stack, the DNA software stack. And what's most important in our use case is the spiking neural network software stack. And so it supports the NAR, which is a neuromorphic intermediate representation. This representation is a data-based flow graph that was designed to enable interoperability between different neuromorphic systems. And so let's say that you are an end user, you have like a model, and you want to run this model on Spinnaker 2 for a certain task. And so you have trained the model, quantized it, and then what to do about this. And this is precisely where NAR comes into play, because it works as a common language for brain-inspired computing to enable an end-to-end deployment on several neuromorphic chips and several simulators. And so in more details, you can check the tutorial on Friday between TU Dresden and SpinCloud Systems. It's a very interesting tutorial. So NAR actually have solved one of the common challenges in neuromorphic computing, which is the lack of a common format to represent models. And so NAR gives a platform-independent format to represent models, SNN models, DNN models, etc. And it supports continuous and discrete times and scales up to support a lot of simulators, a lot of digital and analog chips. So it was designed by Jens Petersen in one of the Telluride workshops, and it acts like the Onyx of the SNN models. So now, after defining NAR as a unifying representation, let's step back and take a look at our complete pipeline that goes from the deployment, the training, all the way to deployment. And so just to be in the same phase, our goal was to benchmark the DVH Jester dataset on the Spinnaker 2 using spiking neural networks. And the goal was to have a minimal accuracy degradation as low as possible. And looking at the architecture of Spinnaker 2, we knew that the model had to be quantized. And at that time, it was not clear which quantization schema or method to use, either PTQ or QIT. So we set out and tested both of them in parallel to see which one gives the best trade-off between accuracy and efficiency. And for that reason, we have designed two models entitled PSNN and QSNN. So the PSNN model was trained in full precision and then quantized with post-training quantization. And the QIT was quantized with the quantization over training. So to design the models, we have combined multiple frameworks like SNN Torch for the leaky layers, Synapse for the pooling operations, Brevitas for the quantized layers, and we use backpropagation through time, surrogate gradients to handle epochs for training. And after designing the models and training them, we had to convert them into an NAR graphs. And in these graphs, we find that they conserve the key computational layers like convolution, like the leaky interrogate and fire, the pooling, etc. And this is adapted with the Spinnaker 2's runtime. So after that, during deployment, we take the PSNN model and we had to quantize it into integer 8 and then deploy it. But for the QSNN model, which was already quantized, so it was directly deployed into the hardware. And to understand this in more detail, I will start explaining the deployment stage. I mean, the hardware setup that enabled the deployment. And then I will go back to see, we will go back to see the two quantization approaches. So starting first with how we made the models run on Spinnaker 2. At this stage, we have the Spinnaker 2 network. So in this network, each leaky interrogate and fire layer from the SNN model was converted into a population. And between these populations, we find projections that define the synaptic connectivity between them. And from the hardware perspective, we find the processing elements in the chip that are low power processing units, and they have a lot of memory constraints, such as the number of neurons that we could fit into each PE. And to meet with these constraints, we have applied a manual partitioning of the network into multiple PEs, meaning if we have if you have a big population, then this population had to be split across multiple PEs. For example, for the first population, we had to set the maximum neurons per core to 900, and so on until, for example, the input, we had to set the maximum neurons for that population, or maximum neurons per core to 17. So after this, we used the PySpinnaker 2, which is a lightweight Python API, to run our models on the hardware. And at this stage, we have 8-bit quantized synapses and 32-bit floating point neurons. So going back now to the two quantization pipelines and starting first with the PTQ. So we started first with looking into the full precision weights, and that are typically in the range of -1 to 1. And then we aim it to map them into the integer 8 representation that typically goes to from -128 to 127. And for that reason, we have calculated a scaling factor entitled lambda s. And the scaling factor is actually computed from the maximum absolute value of the weights. And in our case, we did not use the true maximum, but we have used the percentile-based value. And we have explored multiple percentiles to see which one gives us the best trade-off between accuracy and efficiency. So this percentile function also ensures that we don't fall to the effects of outliers. And so after calculating the scaling factor, we apply it into the weights, and then we quantize them to integer 8s. The same scaling factor was used to adjust the neuron thresholds, meaning that we rescale the neurons firing thresholds from their initial threshold to a scaled one, that is typically multiplying the threshold with the new scaling factor. And so this approach enables PTQ or the post-training quantization to maintain the neuron dynamics of the network. So to wrap up the post-training quantization, I mean, as we can see that it allows to convert our models to integer 8s, and it also allows to rescale the threshold to a more scaled range to ensure that we keep the neuron dynamics and the temporal activity of the network. But as with any method, this comes with trade-offs. So precisely, there are two main trade-offs, which are the use of high percentiles and the low percentiles. So using high percentiles ensures that we preserve the full range of the weights, meaning that we can cover all the possible values, but this could reduce the precision because this could introduce outliers. And on the other hand, for lower percentiles, the good thing is that it smooths quantization, but the bad thing is that we are compressing the range of the weights, meaning that this could hurt the expressiveness. And so to overcome these trade-offs, we have explored a more robust approach, which is the quantization-aware training. So for the quantization-aware training, the model preserved the same structure as the PSNN model or the model from the post-training quantization, but we have exchanged the weight layers, such as convolution and linear. We have exchanged them with quantized linear and quantized convolution from Brevitas framework. And during training, each layer learns how to adapt to low precision constraints. And that's possible by storing both the integer 8 weights and also the scaling factors. And more precisely, these scaling factors were stored in the NAR graphs as a node metadata. And so this method allows to preserve the spiking behavior of the network during quantization by scaling the neuron thresholds using the scaling factor of the preceding layer. And so we start first by applying the quantized layer, and then we compute the scaling threshold, apply the LAF neuron or the LAF layer, and then we get as output the populations of LAF that have scaled thresholds. So this leads us to the section of results. And starting first with the PSNN model that was derived from the post-training quantization pipeline. So this model had a baseline accuracy of 95.07%. And then when mapped on the hardware and run, it achieved a 94% accuracy, meaning with a drop of around 1.07%. And looking at the graph, we can see that the accuracy fluctuates over the different percentile values. And so the low percentiles introduce instability, while the higher percentiles, they preserve the performance. So looking to the 100th percentile, we can see that the model achieves the highest accuracy at this value, which is the 94%. And overall, this gives insights of the effect of the quantization, or specifically the post-training quantization during runtime or during the model deployment. So now to understand the trade-offs between the quantization and performance, let's compare the results from the PSNN model to the ones from the QSNN model. So this model was quantized, as we said, with the QIT pipeline, meaning that the quantization was introduced early in the learning stage of this model. And so the QSNN model achieves an accuracy during inference, or as we call here on-chip test accuracy, equals to 94.13%. And compared to its baseline accuracy, it has a drop of 0.56%, which is a low drop compared to the one from the PSNN, or the post-training quantization. So this highlights a key contribution of QIT, that it preserves accuracy better than the post-training quantization. And there is also a key contribution of the QIT, which we can see from the model size, because with the QIT model, there is a model size reduction of 75%, all while maintaining accuracy. So one of the early conclusions that we can make here is that QIT minimizes the degradation the accuracy degradation compared to PTQ, making it better suited for Spinnaker 2 deployment, or in more particular for SNN deployment on Spinnaker 2. At least we have compared our Spinnaker 2 deployment with other benchmarks from neuromorphic and also conventional hardware for the DVS gesture recognition. So as we can see here, that our Spinnaker 2 implementation for the both models and also from the quantized formats and the full precision formats, so we achieve state-of-the-art accuracy on this task, surpassing some of these benchmarks that are entitled here. And this is specifically using low memory constraints. So this gives insight of the ability of Spinnaker 2 to perform high accuracy for SNN models for tasks like the DVS gesture recognition, which is computationally costly, because we have a lot of spike inputs. So this leads us to the last points. And looking to the work, there are some key lessons that stood out. The first of all is that the neuron threshold scaling plays a key role in preserving accuracy, because as we can see that not only quantizing weights and biases gives the best trade-off between accuracy and efficiency, but we should also account for other temporal dynamics in the network, like the neuron thresholds. And another thing is that the quantization-aware training gives the best trade-off between optimizing the model from the precision side and from the accuracy. So we can say that QIT is the preferred option or preferred quantization method to deploy spiking neural networks on neuromorphic hardware. And what really surprised us was the memory optimization that had a bigger impact than initially expected. And finally, to conclude, where can we go from this? So as we can see that Spinnaker 2 as a neuromorphic system has the ability to scale spiking neural network implementation. And it also opens avenues for using multi-chip scaling. And why not the real-time gesture recognition? So finally, to conclude this talk, we have put all our code in GitLab, the spiking neural network models, the NER graphs, and the deployment on the chip. And if anyone finds it useful, you can use it for other benchmarks or other systems. And yeah, I put also my LinkedIn for any further questions. So this concludes my talk.